breaking all the rules. From Newton to Einstein, concepts elevate. Keep the stream, it's the key to our fate. Dr. Gold dropping gems, knowledge raining down. Actual education making scholars all around. Perpendicular minds, angles sharp as ice. Maths and physics, yeah, the future's real nice. Got the Pythagorean triangles about to flex. Quantum theories on deck, breaking all the specs. Relativity theories, worlds getting small. Grasp the universal laws, standing tall. From the atom to the cosmos, we rolling deep. Grazing up the stars, no time to sleep. Black holes and supernovas, concepts we unfold. Brain power heavy, yeah, that's Dr. Gold. Dr. Gold dropping gems, knowledge raining down. Actual education making scholars all around. Perpendicular minds, angles sharp as ice. Maths and physics, yeah, the future's real nice.
What's up, everybody? Where's my jazz music? Where's my jazz music? There it is. Play. Alright, I think that's working. No drop frames yet. Nice. Somebody didn't mind just chatting. Let me make sure all these are working. Clear that. Nice. This one should be live. Come on. There we go. Should be. Alright, we're really going to test my bandwidth. Let's see if I can also go to Discord. Should be okay, though. Thank you, Sensation. Yeah, the Twitch redemptions work now. During lecture, I gotta remember to turn those off. Otherwise, kids are like, why is he having to chug water during like lecture? No.
I don't know. It's good advice for them as well, I suppose.
It is, yeah. Drink water. Drink water. It's good for you guys. Shithead. There we go. Nice. Good. Yeah. Today was my second day of lecture. I think it went a lot more smoothly. I was having some bandwidth issues at the end there. I know for the last like 5 minutes. Annoying, but what can I do? It's just gonna go out sometimes. I can't imagine it's like. What can I do, Sensation?
You can get tenure.
I could get tenure.
And then you can demand they roll a T3 to your house.
Honestly, I was debating this. Like, if I had a full position at UCLA, I seriously would consider just like dumping my entire thing here over to there, because UCLA. I appreciate that, dude.
Are broken, then it's time to dig them up. I swear it's OBS. Hang on, what do you?
Which is, I can stream, because I'm now streaming to 4 different services. So we're doing Twitch, YouTube vertical, YouTube horizontal, plus Discord. You assume probably about 5. Yeah. But you see if each stream is.
Well, no, because I've run it on 5 before.
Like, yeah, I gotta kill the Discord, because I gotta kill one of them. You can still, no, I can still see you. Yeah, come back, Sensation. Your video's okay. Not many people watch live on Discord anyways. So, I hope people are enjoying things. The classes. Well, the bandwidth will sort itself out eventually. This stream can be accessed in an exit. Yeah, duh. What's up?
Okay, I'll tell you what. Right, here's what I think. Here's what I think you should do. Like as soon as possible. Yeah. Just save what you've got on OBS. Start a new profile and just make it as minimalistic as possible. Just for it. If I'm right, then it'll be without jank.
But here, I'll show you my stats. Yeah, yeah. You have been right before, Sensation, on stuff that I thought like was totally not correct. But if we look at this is my OBS output. My encoding is fine, right? Ever since you came up with the idea that we should go down to 30 FPS, I lose nothing to rendering. I lose nothing to encoding. This is the issue. I'm dropping frames on the network, which if I look at this, oh, that's Kudu. One sec. I'm gonna turn that one off. One sec. All right, there we go. One sec. Okay. No,
right.
It's podcast.
Losing frames on a network could just, like I say, just as easily be trying to push too much information down the stream.
It could be. I think it's the internet though, because it works fine sometimes. But do you see how like it says my bit rate going to YouTube is 600 kilobits? That's garbage. But if we go to, so look, we can look at all the streams that are playing right now. I'm curious if this one will show me. It should say it's connected. Yeah. Oh, so this one's excellent. So interesting. I think what happens is like it just keeps determining who it's going to send like bandwidth to, and that seems to be random sometimes. Oh, because now we're fine. Now we're not dropping any frames. Yeah. It's just this is the problem of the internet in residences. And this is also why, honestly, when we had this whole shift to COVID and like remote learning, a lot of things were kind of fucked because the residential internet services are not equipped to do uploads. They're generally not. It's absolute like shite for upload. The T-Mobile I got is a slightly better upload because with Spectrum I was only getting like 5 or 10 up, which is absolutely trash. Like I can barely support one stream with that. T-Mobile I was getting sometimes like 50 or 60, which is great for upload. I love that. It's just inconsistent and like it'll drop at some points, but like now we're fine. E Raven says I did it all in one day. What'd you do all in one day, Raven dude? What'd you do? A 3-stream streak. Oh, have we had 3 streams today? I think we've only had 2. This is our second one, right? It's our second stream today. This is cool now, but now we're streaming twice a day. Maybe we'll get some more exposure to help teach the people science. So anyways, I would. Yep. Oh wait, now it's not saying it's getting. I don't know. Whatever. We're trying our best.
There is junk.
Yeah, itself out. Nice. Thanks for the follow, non-wizard. I should tell the students just to go to Twitch. I'm pretty sure Twitch takes all my priority.
Well, no, because Twitch was the one that was janking out the most.
Oh, was it? Oh, okay. It'll come back. It's just
it was on YouTube and TikTok, and that wasn't the issue. The issue was Twitch.
Oh, thank God I'm not trying to run TikTok as well, dude. Can you imagine me trying to run like TikTok as dude? TikTok takes a whole other like 4 kilobits, 4 megabits, I guess. Sorry, 4,000 kilobits.
Maybe encoding is the issue.
It's not the encoding. I'm seeing it. It's the network.
No, because so bandwidth, you can't see my hands. I'm better with my hands, right? So
yeah, you can show your video, Sensation. By the way, it's okay to show your video. Just
if you've got a water pipe that can take a millimeter, a liter of water per second, right? Okay. So that's your bandwidth. Yeah. And then you start shoving salt down it.
Yeah.
Eventually it'll get janked up, right? So if you pour less salt, then that will solve the problem, but not entirely. So instead of using salt, I'm struggling with this analogy here. Instead of using salt, you start to use smaller particles.
Is it like this when the landlord starts raising the rent? You know, we're gonna start pouring oil down the sink. Yeah, so I could get more efficient with this, and we did do that because we dropped the frame rate from 60 to 30. I could drop the bit rate even further. I think we're currently at like 4. I could drop it to 3. Because again,
I changed all your settings, but I don't know whether you actually use any of them. I stopped everything from running simultaneously, and then pushed everything towards hardware encoding, and so that might fix it if you try that. But
okay, the file you sent me or something, right? Yeah.
It was me going through all your settings and just stopping everything that was superfluous. When
are you talking about all my sources and stuff? My like sources that were superfluous? Yeah. Oh, okay. Yeah.
I went through them all. Said when you're not using it, stop it. And then I said, right, everything needs to be run through hardware, and hopefully that'll make better encoding.
I'll apply that. Yeah, the encoding is fine. I see it.
Again, just because you don't see the problem doesn't mean it's not there.
That's true.
It says that your encoding is fine, but like I said, if you use smaller particles, in the same bandwidth, you'll be able to push more particles.
We do like pushing more particles. Where's my encoder setting? I'm just curious. Like, what am I outputting at for? Yeah, I'm only doing 3 kilobits on the vertical too. Yeah. All right, whatever. It seems to be okay now. I thank you guys for being patient with me as like we try to figure out technology. I like the fact that I can at least fix as much of the things I can that I have control over. It's been an absolute nightmare for the last like day and a half with like the textbook store not getting the codes out, and then I find out that they're just they're being really shady, honestly, with it, because also they like added it to their thing without my permission, and now I could go on a whole rant about it. And now apparently some of my students are getting dropped from the class randomly, and they think it's an error, and like the department doesn't know what's going on. And I'm like, bro, I just want to teach physics, please. Like, I don't control these things.
What's that thing about, did you really call your son drop tables something? It's like,
yeah. Don't
forget to sanitize your inputs.
Oh my god. Dude, what does someone say? All right, let me see if this works. Wait, does this work? Test. Okay, that chat works. Okay, just nobody's in it. Zach says the bureaucracy. Yeah, exactly. I know this is probably what like Penn Center deals with, because he's like the dean or something, or he's, I don't know, department chair or something. So I'm just a lowly lecturer, I don't have to like deal with that much bureaucracy, but I see it, and it is annoying, because I feel like the executive function of a university should be to teach, not to like deal with all this other stuff. Anyways, you are teaching at a public university in California. That is true. That is, California do have bureaucracy. What's up, Sensation? What were you gonna say?
Did I ever show you that? I've put it in office hours.
How to tame majority?
I'm gonna see if I can calm his temper just a little bit.
What is this?
We should have never signed Michael Owen.
Aye.
Aye?
I've been saying that for years, that like.
Do you see? He's one of the wildest Geordies we've met in weeks.
Who's a Geordie, by the way? What's a Geordie? What is a Geordie?
From Newcastle.
Oh, Newy Brew, man. Newcastle.
So there's the River Tyne, and on one side of the Tyne there's Newcastle, and the other side is Sunderland.
Wait, isn't the River Thames? You guys call it the Times? Isn't it the Thames? No.
No, the Tyne is a different river.
Oh.
The Thames is near London. The Tyne's northeast.
Oh, okay.
Anyway,
I didn't know there were two
yeah. So Geordies are in Newcastle. Mackhams are in Sunderland. There's no real geographical difference. It's just separated by a river. So I don't get it personally, because I don't live up there. But
it's a TV show. Oh, okay, cool. That's actually pretty cool.
There's Geordie Shore. That's also a TV show. Yeah.
Geordie Shore, he says. Geordie Shore is a TV show. Nice. Okay, looks like we do have some questions today, so I'll go over some stuff. And if not, we'll just hang out, talk around. Again, if you're finding us here from UCLA or whatnot, please, feel free. Just in the chat, any of the chats, just start piping off some questions. And if it's homework like you need help with, I'll go over it. Like, we'll do whatever. We're here for you. Okay, cool. Let's start stream. Welcome to Office Hours, main stocks, goals, sexual education. Streaming helps you with math homework, physics homework, science homework, all sorts of fun things. I did have some good questions. Campus Wire. I'm a fan of like any other thing I can use that doesn't rely on, I don't know. Yeah, 2 attempts. Yeah, people
I'm
ask me.
getting a good review of physics from your lectures. What did I miss?
I appreciate that. I appreciate that. Yeah, today we went over basically like manometers. Wait, can you pronounce that for me, Sensation? How do you pronounce manometer?
Well, you say manometer with
Yeah.
like a contraction. So I would say, wait, manometer.
Manometer.
I would say or manometer.
Manometer. Okay.
Yeah.
You say
I would say
manometer.
manometer.
Oh, interesting. Okay.
But you have a contraction. You say manometer.
Manometer. Yeah.
But
Wait,
yeah,
wait,
it's a strange contraction.
Zach says I'm getting a good review. Yes, thanks for Rocket. Yeah, you're more than welcome, dude. Oh, Manamana. Ba 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 ba. Manamana. Is that what you guys were saying in my chat? Sorry, I can't really. I got so much going on in my YouTube chat during lecture that I can't really like look at the Twitch, but I do remember some of you guys saying some Muppet stuff at one point. I was like, oh, that's hilarious. Yeah, I'm glad. Yeah, I'm glad you guys can get a little bit of review of physics and see how I teach. You know, it's fun. One of the we had a cool question that we went over. I kind of maybe wanted to explain better. Where was it? It was. Let me pull it up.
Fuck, it's hot in here.
Yeah, dude. Yeah, we have a heat wave coming up into the U.S. Oh wow, this is kind of fun. So yeah, this was one of the questions we had, which was, you stream your lectures, but they're not on your calendar. Yeah, so they're not on my Twitch calendar. You're right. They're not on my. You know, I could put them on my calendar. I could. You're right. Yeah, let me do that. I forgot we have a calendar. I just don't know like how public I want to get with saying that I'm broadcasting it, like, because this is one of these things where I didn't exactly ask UCLA for permission, but I'll always ask for forgiveness. But in my defense, I tried to use, I think, well, first of all, no one told me what to do. They just said go teach physics online. But I think that the typical way is that people use like a Zoom link, but for whatever reason, like I can't get access to UCLA corporate Zoom, and no matter how much I've emailed them, they don't get back to me. So I say screw it. Like I'm gonna figure out how to at least teach my students. So I'm doing it through like YouTube and Twitch, but I don't know how much I want to like advertise it, because someone might get mad at me being like, oh, well, UCLA owns the IP of you teaching because we were paying you or something. I don't know, like. But yeah, you're more than welcome to come by it. You know, it's like a, you know, it's a side effect of me teaching. It's like, oh, it's on Twitch. Actually, I have to broadcast it on Twitch because that's the only way to get my OBS encoder to start. I don't go to the school itself. I don't. I literally just I do it from the same place that I always stream, which is from my like walk-in closet. Zach asked if I use Piazza. I use Campus Wire. I know Piazza is another one that's pretty cool that people use. It's just my other friend who teaches at UCLA told me he used Campus Wire, and I like it. I used it last quarter. It was great. So we're using it again this time. But Piazza is very similar. Sib says, is there a way to read ahead? I'm kind of worried about the electricity stuff. Yeah. Oh, you mean into the next chapter? Oh, Sib. Okay, yes. So electricity stuff, we're not going to go over for at least like 2 weeks. The issue is that when I release like the textbook content, Sib, I have to also, how Kudu works is I have to release the homework as well. And then I have to put due dates and stuff, and people all get like super worried if they see all the homework out at once. And then I gotta double check, as you saw today, right? Some of the questions have the wrong answer, so I have to go through and like check that first. But if you want to get ahead, if you really want to get ahead, so most of the textbook we use, the Kudu textbook we use, is derived from OpenStax. So let me find it for you. Yeah, exactly. Course management's hard, right? Yeah, that's why honestly I have to release things a chapter at a time, because if I release everything at once, it kind of goes haywire. But okay, if we go to physics, I want to say it comes from University Physics 2. Let me see. Also, I don't agree with how UCLA structures their physics classes. It's kind of whack. Okay, whatever. I don't need to donate. I'm already poor. Yeah, okay, so here we go. So this is interesting. So they do thermo and then E&M in their like physics 2. So let me just like try to explain to people, like, because the quarter system's kind of interesting. So, and then it also changes between the pre-med one and the engineering one. So we're in the engineering track, or the science major, physics major track. But usually, if I were to design physics, here's how I would design physics. So Q1 would be mechanics, just everything in mechanics. Q2 would be electrostatics, electrodynamics, and then magnetism. Yeah. My previous course was for pre-meds. This one's for real people. It's for people who are actually trying to take physics. Although, dude, I had some students from my pre-med stuff say that they're now considering a minor in physics because they really enjoyed my class. I thought that was so nice. Let me go find that kid's email. That kid's email was dope, dude. I need to make like a LinkedIn post about this. Anyways, yeah, this. You know, I'll hide his name because I don't know, like Furpo or whatever the fuck. Hey, look at this. This guy's sent me a really nice email at the end of the year. He said, I ended my second year at UCLA. You've been the most influential professor I've ever had. Before this class, I had little to no interest in physics and was genuinely intimidated by the math. However, you made it relatable to pre-meds. Blah, blah, blah. I'm great. Awesome. Okay, yeah, here we go. Because of you, I'm now considering a minor in physics. I was like, sick.
That's dope.
So I really appreciate the email. Darren, if you're watching this, thanks, dog. I need to reply to your email. Sorry, I've been so busy with everything else, but yes. So, but that was for pre-meds, but some pre-meds are now considering taking physics because it doesn't suck if it's taught by someone who doesn't suck. But wait till they get hit with the physics faculty, bro. This is what I'm saying, dude. Yeah, this is exactly what I'm saying, Fudakai. I know, like, I'm not dumb. I go on Reddit. I view Brew and Walk. I look at the opinions. Most of the physics faculty is a goddamn nightmare to students. And there's a reason why, like, our department has, like, the worst reputation with students, like, taking physics classes. And that's partially why, like, I was so eager to take this, like, position, even if it's like temporary. It's because like I want to like change that opinion, because physics is really cool if it's taught by someone who actually wants to teach. Yeah, Zach says his math department also had a reputation. Yeah, it just happens, and it's because universities get into this weird quandary of, you know, focusing on teaching, which is kind of like, you know, what they consider basic subjects that are beneath them and they don't really want to go into, versus like conducting cutting edge research, because that's how the grant money comes in. A ticker shout out. Oh, okay. Tell me what the ticker shout out you want. I'll do it for you. So yeah, so I understand, and I'm trying to like fix that. We'll see. Anyways, this. Yeah. Yeah, exactly. They think they're immediately on your level. Yeah, that is the thing. Again, because most physics professors are fucking geniuses. You do have to be very, very smart to get a position at UCLA as a professor. As like a full-time tenured professor. Also, it's brutal to like even just get tenure. You have to be really, really intelligent. And you have to do cutting-edge research, and you have to be able to pull in grant money. The teaching aspect is not as emphasized. And the problem with like when you get so smart and so specialized is you kind of lose touch with how to explain things in simple terms. and then you know, and then it creates a bad experience for undergrads. So what they've been experimenting with, and they've done this at UCSD and some other UC schools, are what they're calling teaching professor positions. So where they're now hiring professors on a same tenure track level, but your job is just to teach. And I think that's a great like little band-aid to like try to, at least for the intro classes, not scare everybody off from physics. Whatever, you can have the hard-ass Soviet Russian, you know, genius teaching quantum field theory, because at that point, yes, you if you've made it that far, you've probably developed enough skills that you can go toe-to-toe with these upper division professors who are, yeah, they're geniuses, and you have to be able to speak that language. And, you know, I don't want to sugarcoat things. If you want to go to grad school and do physics research, you have to be at that level. But for these intro classes where kids are just maybe thinking about getting into physics, or they need it for like their pre-med degree or something, I think they really should like supplement that with professors that, again, I don't do cutting edge research. I don't write awesome grant money, whatever the fuck things. I like to teach, and I like to teach really basic concepts in ways that make sense. So, how many physicists do we really need? I don't know, how many does it take to screw in a light bulb? Anyways, okay, so this is how I would design physics. Sib, to get back to your question, because I just want to show you like why it's a little confusing how the quarters work. And then I would do thermo, waves, optics, and I don't know, sometimes we put in like some special relativity in here as well. Yeah. Like quarter 3 is always what I call kind of the grab bag of physics. It's just a bunch of like random cool topics. But your bread and butter in physics is mechanics, and this is called E&M. Yeah, you're right, there is some nuclear in here as well. Yeah, totally right. Again, this is kind of just a grab bag. However, how UCLA works is they've now taken, I think it's electrodynamics and magnetism, and then they've replaced this by putting, oh, also there's fluids here. They're now putting like fluids up here and waves up here, and then they're putting this like over here. And I don't know, I think to divorce electrostatics from electrodynamics and magnetism, it's kind of weird. What they really do is they do it this way. You'll see how it's really topsy-turvy. They put fluids and waves at the first thing of quarter 2. Then they put electrostatics at the end of quarter 2. And then electrodynamics, magnetism at the beginning of quarter 3. The issue here is that there's a gap in between this, especially if you took physics 2 in the spring and then you're taking physics 3 in the fall. That's a whole summer you lose. Particle physics and condensed matter, those are upper division courses. This is like what I call like physics 101. Physics 101 track. Okay. Anyways, so the current UCLA way of teaching physics is, I think, a little topsy-turvy. But if, Sib, you want to get ahead, the electricity stuff we're gonna do. Sorry, there it is going to be this. It's going to be chapters 5, chapter 6, chapter 7. Oh, we also do 8, 9, 10. Yeah, okay, here you go. So this is what it's going to be. Yeah, they also throw circuits in there. It's weird. I really don't like how they do this. But whatever. I didn't make the curriculum. So this, Sibley, this is what we're going to go over later in the course. Are going to be these topics. And if you want, let me get you the chat. Let me get you the link for that too. Here, I'll dump it in the Twitch, and then I'll dump it in here. Would some of the answers be wrong on the homework too, or just a problem with the clicker? I hope they're not wrong with the homework, Mistral. But if they are, please let me know. And I'll work my best to sort everything out. Again, if there's any errors or anything wrong with whatever, I'll manually go in and fix it. That's the advantage of this versus mastering physics. If something's wrong with mastering physics, I send them an email and they get back to me in 5 to 6 business weeks. And then the course is over. But I was given this course by another teacher who literally taught it last quarter. So I assume everything is correct. But we may find things that are wrong, and that's okay. It's learning is a imperfect process. But that's you know, it's the friends we make along the way. Is that what we say? That's all the fun. Oh, good. Electricity stuff for 1B. Yeah, so I just sent it there. So that link right there, OpenStax, Volume 2, and then you're gonna want to look at these chapters 5 through 10, because we're not gonna do electrodynamics. Or magnetism. That would be Lenz's law. And, yeah, that's magnetic fields, electromagnetic induction. This stuff is all really cool. I love this stuff. E&M was my favorite part of physics, and that's why, like, I went into, my PhD of plasma physics, is I really liked E&M. Took Physics 2 last semester. It was brutal, not enjoyable at all. I'm sorry. Yeah. I mean, probably did you have a bad teacher? That's my question. Atomic physics is also an upper division course. Yes. Yeah. We don't really do much atomic physics in the undergrad track. Or sorry, we call it like the 1 series. You know, the 101 series. Lower div. There we go. Lower div. It's called lower div physics. And then here, there you go. There you go, Fedekai. That's it. Sent you the link. This was a cool question we had. I just want to go over it real quick. Because I wanted to explain more about this, but I ran out of time. Because I only get an hour and 15 minutes. Ask and he shall receive. Oh, nice. So, okay, they said a snorkel is a U-shaped tube used to breathe with your head underwater. Assuming you build a very long snorkel so that you can breathe at a depth of 33 feet. So here was a cool thing. We figured out that 33 feet is 10 meters, right? What would the pressure difference be between your lungs and the water around you? And then they say, warning, this is extremely dangerous and should never be attempted. And I'm going to go over, like, why it's extremely dangerous to do this. So, first of all, does anybody know, like, how we breathe? Like, how do we force oxygen to get into our lungs? It's pretty cool. Yeah, we take a Do you know, Sensation? Do you know how we breathe? How do we, like, get oxygen in?
Your diaphragm forces up and pushes your lungs out.
Yes. Okay. Good.
To breathe
yeah,
out,
like,
and then. No, yeah, to breathe in. Yeah, I know it's to do with your diaphragm, the bottom section of your lungs, because your diaphragm fits in that space. But I can't remember the specific.
So Jeff has also So we expand our lungs, and in doing so, we create kind of a partial vacuum. Really, what we do is we create a decrease in pressure inside our lungs. So when here, I'm gonna put. Let me make my man. Jeez, you didn't have to flex. Sorry, famished. Okay. So here, whatever. Person, and I breathe in, right? Okay. I'm really glad we can breathe without. Yeah. What's the? There's something that's responsible for that. What's it? Our cerebellum or something? I don't know. That's what the pre-med should tell me.
What?
The thing that's like responsible for like us just breathing naturally without having to think about it.
The medulla oblongata.
There we go. That sounds pretty good.
Or is that
suddenly
emotional?
I'm aware of my breath? Yeah, the lizard brain. Yeah. Okay. Yeah. So here's what happens when we're just chilling here, right? Okay. What happens is that the pressure here. So if we looked at like the pressure. That's just equal to P atmospheric. It's equal to atmospheric pressure. And the outside air, right, is also equal to P atmospheric. And then when we breathe in, what we end up doing is we end up like expanding our diaphragm, okay? Like we're expanding the volume there. And if you remember from chemistry, or if you've taken chemistry, right? PV is equal to nRT. Whatever, you can get rid of the R's and stuff. So you just get like PV is proportional to T, but T is also constant. So we end up saying like P1V1 equals P2V2, okay? So if you increase the volume, you decrease the pressure in something. So when you expand out the volume of your diaphragm, when you make your lungs bigger, as long as you're not changing the temperature or you're not like whatever, you're momentarily going to create a lower pressure environment, okay? So now, here, P is less than P atmospheric. And because there is less pressure in your lungs than there is outside, this creates a pressure differential in which oxygen flows into your mouth and down into your lungs. So, yeah, what you're doing is you're lowering the pressure inside your body, and that's what creates kind of like motivation for the oxygen to enter your lungs. Okay.
Nice.
So, they're saying like, okay, but now let's say that I took my person here, right? And we decided to go underwater. So, let's say we're underwater here, right? And they say I have like a snorkel tube, a little snorkel tube. Okay, that I'm breathing air in, okay? So, because I'm at a, yes, nitrogen, CO2, yeah, that is true. Actually, most of what we breathe is actually not oxygen, right? I think it's mostly nitrogen. Anyways, okay, so this is a height equal to 10 meters. And what we learned in the class is that anytime you have, like, a body of liquid above you, that creates pressure. And that pressure goes out in all different directions, but it's dependent on the height. Oh, 78% nitrogen. Wow, that is big. So, at a depth of 10 meters, you have a pressure here that is equal to, we're going to say, like, rho GH, plus there's already, right, the atmospheric pressure up top. Okay? And when we solved for that, rho is around 1,000, G is around 9.8, H here is around 10 meters, and then we say plus P atmospheric, which is 101 times 10 to the 3. This ends up being basically 100 times 10 to the 3. Oh, does it? Wait. Oh, yeah. Wait, which homework says unlimited checks? Is there stuff that's not multiple choice? If it's not multiple choice, I think you get unlimited checks. As to why it's putting random answers, I think there's something, I've heard this before, there's something up with if you're using Grammarly, or if you're using one of those plugins on your browser that like tries to autocorrect text and stuff. I think it just starts fucking with it, is what it does. I think they have something about it. So if you have Grammarly or some other like add-on, I think that like messes with it. Technology, man, dude. No one can get anything right, dude. Anyways, so what you end up getting is that P here is equal to 2 atmospheres. This is called an atmosphere. I don't think I actually said this in my class, but 101 times 10 to the 3 kilopascals, or 101 times 10 to the 3 pascals, or 101 kilopascals is 1 atmosphere. So you basically get another atmosphere from being underneath 10 meters of water, and so now you have 2 atmospheres of pressure. And that 2 atmospheres of pressure, right, is now acting on your lungs, okay? And let's say, for instance, you have air in your lungs that's equal to, like, 1 atmosphere, right? That means the pressure difference between it, right? Like, the difference in pressure is now only a single atmosphere. So you have 2 atmospheres pushing this way. You have 1 atmosphere pushing this way. So you already have like -1 atmospheres inside of your lungs. So you have to provide another atmosphere in order to be able to suck oxygen down, which is difficult. Let me see. There was some like right. Yeah, your lungs are being crushed by 2 atmospheres. So in order for there to be enough pressure to pull down something that's already at 1 atmosphere, you're already having to fight an atmosphere. So you have to compress your lungs another atmosphere just to even get like break even. The record free dive is 253.2 meters underwater. Yeah. Oh, so you can't. Yeah, exactly. Yeah. So if you lower your lungs to 0.9, right? It's effectively 1.9 atmospheres. There's still more pressure down here, right? Than there is up here. You got to drop it down another whole atmosphere in order for there to be any sort of differential. And then apparently, pulling in air against a 1 atmosphere pressure difference is like trying to suck a milkshake through a 100-foot straw made out of concrete. What? Wait, what? Anyways, in any sense, your lungs are like not that good. Yeah, your lungs don't have enough strength to expand out to fight an atmosphere, 1 atmosphere pressure differential. So, your chest can't expand, no lung enters your lungs, and then you die. So, you would suffocate. And yeah, you just can't inhale. So, the reason why this works with like scuba divers and whatnot is that the air that is being pushed in is pressurized. That's why it's in tanks, right? It's not that they just have like ambient air inside the tank. That air is being forced out at a higher pressure than 1 atmosphere, and it's usually matched to be whatever the water pressure is. So I would imagine, I've never scuba dived, but I think that the regulators like that people use in order to breathe underwater, those must change the pressure of the air coming into your lungs depending on how deep you are. I think that's pretty cool. Let's see if that's true actually. What is it? Scuba regulators change pressure based on depth. Yeah, scuba regulators are designed to change the pressure of the air they deliver based on the depth of the diver. That's very cool. So as the diver descends, the ambient pressure increases, and the regulator adjusts to provide air at the same pressure as the surrounding water. This ensures the diver can breathe comfortably and without resistance at any depth, right? Very cool. So you said the record free dive is 253.2 meters. So I guarantee you they weren't breathing. You can't breathe down there without having pressurized air being thrown into your lungs. Also, they would be experiencing 25 atmospheres of pressure. Like 25, they would weigh 25 times as heavy. That's crazy. Yeah. Very cool. Anyways, yeah, I hope that makes a little bit more sense with, yeah, pressure, and stuff. The record with gear is 332. Yeah, just at some point, bro, like, your body just, like, can't take it anymore. It's just like, no. Yeah. Matthew says, I picked my A levels for next year and year after, chosen physics, chem, maths, further maths. Am I cooked? I don't think so. And again, if you ever need help, you know, you have a great community here on Twitch that can help you out with math, especially further maths. Like, you know, you got Zach, you got Penn Center, you got, I think Eric. Is Ian Stuckey? Is he streaming again? I think I saw like some late night, midnight stream from him or something. And I was like, oh, Eric's back. And it's always growing. So, yeah, the resources are infinite. You just gotta, you know, get the help when you need it. And I can help you with physics for sure. And chem. I like chem. I'm a big fan of chem. Sensations. Like, you need to drink some water.
It's hot in here, and I've got a big room.
Bro, I'm cooking,
Dude, I'm at 80.9 right now. I got baby voice going. Okay. That's funny. Let's see.
Let's see if I can compensate the baby voice.
Someone had a good question about this, and I really liked this person's answer. Let me pull this up. Someone asked this in my class. Humans are so bad at diving. Yeah, they're literally the worst thing.
Dude, I watched that, what was it? It's called The Rescue. It's about the Thailand one, the cave diving stuff. I was like, nope.
Oh, no.
No. I'm not. Dude, I don't understand people that go cave diving. Like, bro, you have a death wish. Like, what's going on? Dr. Gold, are you friends with Alvin, Simon, or Theodore? Which chipmunk would I be? I want to say I'd be Simon. I'm pretty sure I'm a Simon.
I don't disagree with that.
He's the nerdy one. Isn't Simon the nerdy one? I feel like he is. Anyway, someone had a good question about this one. So we were talking about manometers, manometers. And yes, thank you, Famish, for letting me know what like a datum was. I now understand datum is just a reference point that you measure height from, which is pretty cool. So yeah, what we learned in class here, right, is that if you have like a tube here and it's open to both sides, then the height of the waters will be the same, right? And the reason for that is actually kind of cool. If we consider this, let's consider this point right here, right? Let's consider this like h is equal to 0, okay? Then if the fluid is still, right, it means that the pressure from here has to be equal to the same as the pressure from here in order for them to cancel out and the water doesn't move. So we know for anything that is open, there is atmospheric pressure pushing down. And then also we have a height of water, which is here. And this column of water exerts pressure, which we learned was equal to rho g. And I don't know, let's just call this like h1, for instance. Let's say that like this distance right here is h1. Well, this also has the same thing. Also has P atmospheric. And then this is rho GH2. Let me get a different color for that. Yeah, let's do this. Now, in order for the pressure here to equal the pressure here, like mathematically, right? That just means that on the left, P atmospheric plus rho GH1 has to be equal to P atmospheric here plus rho GH2 in order for things to be at equilibrium, to be still, right? I need the pressure from both sides to be the same right here. Obviously, atmospheric pressure is the same on the left and the right, so that goes away. And then we're left with this, and if the density of the fluids are the same, that goes away. This goes away, G is the same. And you just get the H1 equals H2. So you get that, yeah, cool, this height equals this height, and that's why these two sides are at equal height. Makes sense. Okay, but now let's make things a little bit more tricky. Yeah, does the second diagram also explain why we can only suck soda up, so far up a straw? Yeah. So, yeah, let's consider. Yeah, you want to do like a straw? Let's just do a straw. I think it's a cool one. Let's do it. So let's say, for instance, you have some soda. And then I need a straw. Let me make a straw. Okay, here's my straw. There we go. And we're going to try to, like, yeah, suck the soda up, right? Yes, this is how old-fashioned barometers work. It is pretty cool. So, yeah, we have the soda being sucked up. And let's say, for instance, it's being sucked up to some height here. And we're going to call this height H, okay? And then we need our person. Let's make our little person. No, person's not a square. There we go. There we go. Okay, they're sucking on the straw, right? Okay, cool. Okay. And let's say that this is, that, you know, the glass is open to the atmosphere, okay? So if we consider, right, our datum, which is going to be... Some people believe sucking is a force and that you could suck without limit. Well, I think as we showed earlier with the scuba diver stuff, right? Sucking only comes from expanding your diaphragm out and creating a pressure difference. And I think there's only so much of a pressure difference you can create with your lungs. Like, your muscles are only so strong. But yeah, okay. So here, let's say, like, looking at the outside, right? You only have one thing pushing down on it, right? And that's going to be the atmospheric pressure. Okay. This pressure must also be the same as the pressure over here, right? Here, however, right? Let's see what we got. We have rho G H1, right? And then we also have whatever the pressure is from our mouth sucking on the straw. And this will not be zero. Like, you cannot create vacuum with your lungs. You can create a low pressure, but you can't create a negative pressure. So we're going to call this like P sip. I wanted to say P suck, but that gets weird. So anyways, P sip, right? Okay. Okay. Even if you could create a vacuum, there'd be a limit. Well, let's see mathematically if that works. Okay. So anyways, so this is a downwards pressure. It's lower than atmospheric, but it is a pressure. So if we were to equate this, right? I then have that, like, P atmospheric, which is the pressure here of it just pushing down, has to be equal to rho G H1 plus P sip. So we know atmospheric pressure is 101 times 10 to the 3. We can approximate soda as having the same density as water, because most soda is just fucking water, honestly. And like sugar. So that would be equal to 1,000 times 9.8 times whatever the height is, right? And then plus the pressure of my sip. Okay. So let's see. Let's plug in some numbers. Let's just figure stuff out, right? Actually, I think here's what I want to do. I want to figure out what is the highest pressure the human lungs can provide. Let's see, what is the highest pressure human lungs can create? Okay. Well, it's funny. They give the answer in centimeters. They already give the breakdown. I don't want that. Man, give it. All right, they say 2.8 psi. Here we go. So let's do 2.8 psi to kilopascals. So 19.3. Okay. So sipping pressure, like the maximum you can do, is equal to 19.3 times 10 to the 3 pascals. Notice how this is this is a lot less than 100 times 10 to the 3, right? It's about, what is that? That's a fifth, like 20%. So your lungs can create an environment that is 20% the pressure of your outside surroundings. So if we were to plug these things in here, so we get 101 times 10 to the 3 is equal to 9,800 H plus 19 times 10 to the 3. Okay. If we subtract that over, right, what do we get? We get like 80. I'm just going to call it 80. 80 times 10 to the 3 is equal to 10,000 H. Or let's say like 1 times 10 to the 4th H. And then if we divide it... I don't get... They get 200 milliliters? Is that what they said? Oh, wait, 200... Oh, wait, so that's... sorry, expiratory pressure. Sorry, that's pressure pushing out. Sorry. Minimum pressure... is 2.8. What is it for sucking? Oh, it is 2.8. Okay. Yes. Okay. That's why it'd be flat. Because it's less. Cool. Yeah. Yeah, so actually the maximum it would be a barometer. So if, for instance, this was closed to vacuum, Jeff, which is how, like, here, let me get a picture of a barometer. And then we're going to get the amount. Here, but I'll show you. Water. This is the classic barometer they use. Well, it looks a little phallic. Something that doesn't look so weird. Yes, but mercury is much denser. Correct. Yeah. Yeah, they don't use water. I mean, you could, but it would be a lot longer. You're super right. You need a very big. You need something very big, but they kind of work on the same concept. So, yeah. Basically, right? If this is 0 because it's at vacuum, right? What you do is you basically, like, you tip this tube, you fill it with liquid, and then you tip it upside down, and so that no air can get in. But the rho GH of this has to end up equaling P atmospheric. And because here, let me use a different color. Here you got P atmospheric. And then here you just have rho GH. Pressure has to be the same at both. And then I think, what's the density of mercury? It's kind of cool. We can come up with this. Density of mercury is 13,534. So you have 13,534 times 9.8 times H is equal to 101 times 10 to the 3. Yes, it should. You're correct there. You're correct. Where's my calculator? Okay. So if we do this, watch. If we do 101 e to the 3, and then if we divide it by 9.8, and then we also divide it by 13.534, we get 761. Oh, and 761. That is barometer in millimeters. Yeah. Wait. Oh, sorry. It wasn't 13.534. It was 13,000. Sorry. Oh, yeah. Okay. One sec. 13,534. There we go. Okay. There we go. 0.761. My bad. This is a comma. Yes. 0.761, right? Meters, which is 761 millimeters. This is also what they call 761 torr, which is also equal to 1 atmosphere. I think, actually, they approximate this as just 760 is what we say. So, yeah, when we measure things in torr, yeah, it's because we're saying how many millimeters of mercury would be pushed up a tube or could be supported up a tube by atmospheric pressure. So, wait, so going to our soda thing here, right? So we said that was that. Okay. So I want to get answers here. So 80 e to the 3 divided by 1 e to the 4, and that gets us 8. Okay. Cool. So I guess, yeah, 8 meters is what you could suck up. Which, wow, that's kind of a lot, right? Yeah. Okay, cool. About 25 feet. Yeah. That's a lot. 25 feet. So, I mean, you can suck up a lot of liquid, apparently. So, from a third-story building, probably not. Yeah, I agree. Yeah. It's kind of cool. You ever seen, like, those crazy straws and stuff? Right? Anyone remember these things? Crazy straws? Dreidel-shaped Dude, what? Don't do that. Oh, no. Okay. Yeah, these, like, wacky things, man, right? It's super cool. Anyways, yeah, so these technically aren't harder, I guess, to suck up as long as the height is the same. It's a longer path. It just takes more time. But in terms of, like, the pressure, it shouldn't be different. I guess technically you would have cohesion between the liquid and the whatever, the surface of the plastic. But ignoring that, if you just looked at the physics pressure point of view, it should be the same. Yeah. All right. Oh, one sec. Sorry, I haven't checked any of my office hours. Okay, no, we're still good. Okay, someone had an interesting question here. Does this also mean if the air pressure is less than 19.3 kilopascals, you couldn't breathe at high elevation? Ah. Let me think about that. Because, yeah, you need to create less pressure, but now it's easier for your diaphragm to expand, right? Because you're not fighting as much. your lung pressure couldn't become lower than that, so you can't force air to move in. I think technically, yeah. Ugh. Yeah, let's see. And that happens above, it looks like around 12,000, 13,000 meters. Or 15,000 meters. Okay, cool. Yeah. So apparently around 15,000 meters, atmospheric pressure drops to 19.3 kPa. That's what I'm reading here. Which, yeah, that is higher than Everest, right? Yeah, that's much higher than Everest. I think the main issue is that the air just becomes thin when you're hiking these mountains that are so tall. And so it's not even that you can't get the air in, it's that the concentration of like usable gas for your biological functions is so low that you would just be like heaving, just trying to get the amount of volume to come in. And then that's like a self-fulfilling cycle of doom, right? Because now you're having to expend more energy in order to just breathe really quickly. Yeah, because the same volume has... Exactly, the same volume has fewer moles of air. Correct, yes. Yeah, that's pretty cool. Ba-da-da. Let me see. Let me see. I think someone else had another campus. Right. Yeah, good. Sure. What do you want to ask about static versus kinetic friction? Yeah, that's really cool. It usually has to do with work. It's the work done is what it is. Also, what is it? Someone's asking. It turns out that atmospheric pressure always cancels out. And yes, Sib, this is correct. Yeah. Anytime something is open to the atmosphere or open to, yeah, then you always have outside atmospheric pressure that's acting on it. So Jeff says, when it goes from static to kinetic, isn't there an instantaneous non-zero acceleration? Correct. I mean, right, because acceleration is equal to, right, change in velocity over change in time. So your velocity has to change because this is also equal to F over M, and now your force is changing, right? Should that be impossible? Yeah. I think if we think about it on like the infinitesimally like small level, friction is like a bunch of little teeth, right? If you look on the microscope level of like two surfaces, they have teeth. And when those teeth are like locked in with each other, right? They provide enough force to keep them together. Eventually, that force is not enough because you have an outside force that's pushing so much. And so what happens is like some of the teeth start to like break And as that happens, now you start getting a change in your velocity, which you definitely have an acceleration. I think eventually what it comes down to, Jeff, is that there is like the refresh rate of the universe, which is called the Planck time, right? Have you heard about this? This is like the minimum amount of time it takes for something in the universe to happen. Yeah. So time is discrete, so dvdt must be infinite. Yeah. That's going to extreme. Yeah. Definitely is. Oh, the actual feet. Make more money with actual feet. Someone else had another cool one. Let me see. I think it was this. Which I think this always comes down to like conservation momentum. No, not this one. Where is it? I'm trying to show that the coefficient of static and kinetic friction should be equal. Yeah, the issue is that like once something starts moving, once it's like it's over the threshold, Jeff, now it's not able to provide as much force backwards. People have summer school, Sebas. Yeah. So, someone just like dumped this screenshot in my in my channel, and I'm curious what they're asking about. But I think what you have here is you have a wedge here, and then you have another wedge here, and they're smooth. So what happens is like this one slides down this. Oh, is this? Oh, nah. Yeah. Here's the question. Is this fixed? Because what sometimes happens is this is also like frictionless, and you end up getting like this thing moving to the left while this thing like kind of like moves to the right. But the momentum has to be the same. I have summer question to do, so why did I question it? I don't know, like most people don't have school. You're right. Yeah, that's my question here. Is this I feel like this is like What's up, Jonghyun? But then there's also like a particle. Does the particle move as well? Yeah, Jaden. Yeah, I remember you, Jaden. I remember who you are. I'm curious what this question is. There's another one about this. Let me go find it. It's like wedge top of inclined plane smooth. Let's just see if we can find it. I know this is a classic question that gets yeah, there you go. It's a JEE question, of course. Dude, JEE questions are just like difficult for no good reason. They just like want to like cause pain. All right, so let's see. What is this JEE guy saying? A wedge is placed on a smooth surface of a smooth incline having with the horizontal. The vertical wall of the edge has a height h. And there's a small block also. What's up, Don? Go shout out to Don. Thanks, Don, for the raid, dude. Don Factorial. Thanks, dude. So yeah, let's see. This dude ends up writing out a bunch of forces. There's also a normal force, right? Acting on block 2. What's up, dude? And then... Interesting. He's defining MA that way. Oh god, this is getting like really weird. Oh, but there is friction between the block. Oh. Yeah, I don't think I'm actually gonna attempt this one just because I don't know, those questions like hurt my soul. There's so many different normal forces and stuff going on. Hey, let me make sure it was his. Because all I got, from the student is they just dumped this on me. I was like, okay, cool. What are we trying to solve for? Are we trying to? I mean, is there friction here? Said this is smooth, so I assume that. But then if he draws lines here, usually that means this is fixed. But then yeah, so here you can. Here, I can like start to do a little bit of it if you want. It's okay. Try to explain what's happening. And then you have the wedge. The wedge. They also, I believe they need to tell me the height of this wedge. Yeah, there's a lot of information not being told here. Oh, they tell me the length of the wedge is 3 meters, though. Okay, so we can actually figure that out. Watch, I'll show you. That's actually kind of cool. Okay, yeah. So, if this right here is 37 degrees, then this is also 37 degrees, right? Because it's, you know, we assume it's parallel to it. And then if this is 3 meters... I know this is a... Man, it's close to a 345, right? But it's not. Isn't it 30? Isn't it 37, 63, 90 for the 345? I believe it is, right? Yeah. Yeah, look at it. Yeah, the 345 is, sorry, 36. It's 3753. Man, but they put the 3 over here? No. Bro, why would you do that? They should have made this the 4. Yeah, this should have been the 4. Or they should have said that the height of this was 3. Okay, you know what? I'm just going to say no, dude. Because I don't want my life to be difficult for no good reason. I'm going to say that this is 4 meters. And then this is 3 meters. So then I know that this distance here is 5. I don't know, I feel like it'll just help me out later. What's up, 1K? I got your email, by the way. I got to figure out how to get you Cyberpunk. Do you need it specifically on Steam? I see it on, like, GOG or something for, like, there's, like, a sale on it. Also, I thought you don't have a gaming PC. I thought your parents forbid you from playing video games. How are you going to play... How are you going to... Cyberpunk's a very intense video game. You need a pretty beefy PC to play Cyberpunk. Anyways, okay. So there's going to be And then there's also the particle, which is 2 kilograms. Okay. So this is gonna have, we're gonna say like, this is gonna be 19.6 pulling down, 19.6 pulling up. Do we know the mass? Oh, we know that's 4. Okay, cool. 4 times 9.8. Is that 37.2? 37.8? Okay. So then we have... $39.2 coming down. But the normal force is up at that angle. Okay, very cool. There's actually a lot of interesting forces on this. Because then we have this as well. Oh, man. I didn't draw this exactly, right? Let me draw it better. There we go. Free body diagrams. Okay. This right here is 39.2. We're just going to say sine of theta. And then this is going to be 39.2 cosine. And you know what? I'm just going to fucking... Well, no. I'm tempted to just use 10 for G. I really am. I actually want to. Just to make the approximation like a little nicer. Because I think we have nice numbers here. Whatever. This is 20. This is 20. This is going to be 40. So then this is going to be... 40 sine of theta. And then this is going to be 40 cosine of theta. Right, which, yes, here's the cool thing. So for a 3, 4, 5, because I recognize this is 37, 90, 53, that means sine of theta is equal to 3/5. Cosine of theta is equal to 4/5. Tangent's equal to 3/4. So very cool. Yeah, that's nice. So 3/5, yeah, 120 over 5 is 24. Yeah, look at that. So this is equal to 24. This is equal to 32, right? Yeah. Cool. Okay, but let's consider this block, because there's some weird shit going on this block. Yeah, actually, what frame do I want to do this in? Because, yeah, do you see how I also have to then break this up into components? Yeah, okay. All right, whatever. Okay. So here, we got 32 pulling down. We got 40 pulling to the right. And then we have normal force pulling up here. This is force normal. And then from the red also has, like, this acting on the block is going to do an additional... Oh, it's just going to be half, right? Because that's going to be 20 sine theta and then 20 cosine theta. Okay, cool. So then we're going to have an additional 16 and 12. Okay, cool. And I think they said everything's smooth, right? Yeah. Okay. My question is like, what's the problem? Are they just asking like how far does it how long does it fall? Because also I don't even know like I don't even know. They didn't give me very much information here for this. But okay, because then here let me show how you could also like break this up. That 40 should be 32. Oh wait. Sorry, that should be a 24. Thank you, fam. Yep, I got a little ahead of myself. Yep, because then this can also be broken up into. Here, let me move this over. Over here. Make like I want like a slightly different color. Make like a slightly less red. Ooh, like a salmon? Yeah, let's do salmon. Kind of weird. Right, and then this one was 12. 12 and then 16, I think is what we said. Yeah. Yeah, cool. Okay. So that's all the forces on the wedge. And then we assume that the normal force will be whatever it needs to cancel this out. So then from that, yeah, you could figure out how far it takes for the thing to fall down, I guess. I'm confused what the question's actually asking here, but that's how you set up the force diagrams. I think in this JEE problem, they had kind of a weirder thing. I don't want to watch ads. You know, if you ever want to get rid of ads, just put a period after .com. It'll get rid of it. In this question, they said there's friction between the block and the wedge to prevent slipping, okay? Assuming there's no friction between the block and the wedge, calculate the time which the block will hit the incline. Oh, okay. Yeah, just after the .com. Yeah, if you do .com dot, it'll get rid of the ad. It's kind of a cool little trick. Oh, I see. Yeah, so the cool thing is you can figure out like as the block moves down, I believe as the wedge moves down the incline, if there's no friction between the particle and the wedge, then the particle technically like moves to the right with respect to so watch what so like as this thing falls down, right? This thing, if there's no friction on it, right? Notice how this thing only has up and down forces. This thing should stay stationary in the left-right direction. It will start moving down, right? Because as this thing, like, moves down, this moves down. But eventually you'll get to the point where the wedge is, like, right here. And at that point, the block is now touching the incline. So all you really have to do is figure out how much distance it takes for the wedge to move whatever, this 4 meters horizontally. And to get that, interesting, you then want to convert what that distance horizontally is diagonally, and then your diagonal distance would come from this. Okay, cool. That's a cool question. I don't think you need a 16-minute YouTube video on it. That's a lot, dude. I think also this one was weird because they had a frictional force. Which I think, wait, it's part C. Let me see if they do part C. That's A, B. Go to part C. Do they ever do part C? Yeah. JEE questions are like nightmare level hard. You will never have to do anything this difficult in not even like college. This is just like India's way of like trying to filter out the billions of people they have trying to escape poverty. They just make some ridiculously difficult exam that everyone it's really it's a real struggle to see like who really wants it, like who really wants to escape. But you know, it's like going to the gym. You know, it's like really heavy weightlifting, I guess. Let's see. Any other questions from Campus Wire? Cool. People asking about final exams. Love it. Okay. All right. We do have a couple web screenshots. Ooh, nice. Thank you, Mistral, for submitting this. Sorry, I didn't see it earlier. Always bug me in chat, Mistral, if I don't go through it. Let's see. Consider the automobile hydraulic system as shown. Suppose a force of 100 newtons applied to the brake pedal, which acts on the pedal cylinder acting as a master cylinder through a lever. A force of 500 newtons is exerted on the pedal cylinder. Which, wait. Why do we have two different forces? Oh, I think I see what's happening. Oh, because it's a lever. Yeah, okay, cool. So, dude exerts 100 newtons this way. That creates like a torque, is what it does. Which, yes, if the distance here is 0.2, I believe that, yeah, that's the same thing as there being a 500 Newton force here. It's a factor of 5. Okay. Or no. That's 0.2 to there. Oh, okay, one second. Let's read all. This is good. This is question 1 of the homework. Oh, God. Okay. The pedal cylinder has a diameter of 0.5 centimeters, and each wheel centimeter has a diameter of 2.5 centimeters. How much pressure is transmitted in the hydraulic system? In atmospheres. Okay, cool. So this goes into pressure is equal to force over area, and it looks like I have 4 different forces that eventually are getting exerted, right? But we don't know what F2 is yet. One sec. And then I think is this a multi-part question? No, it's just a 1-part question. Okay. Oh, I think, okay, first of all, the total pressure that's exerted here has to equal the total pressure here, considering if we assume this is a incompressible fluid, okay? I think they're giving you way too much information here. They're making things complicated. Because what I see here is that 500 newtons is exerted on the pedal cylinder, okay? So you have a 500 newton force here, right? That you're pushing in with. This, I don't think we really care about this. I think it's a cool engineering thing, but they're basically showing that like a pedal allows you to exert more force on a cylinder. But, okay, so you just have 500 newtons divided by the cross-sectional area of that cylinder, which is a diameter of 0.5 centimeters. So you can have 0.2. So this is over pi times 0.25 times 10 to the minus 2 squared, pi r squared, right? And that pressure there should be the same pressure everywhere else. It's going to be a different force, which is cool. So we'll show you how that works. But let me see if we get the right answer, because I have the right answer. Divided by pi. And then we're going to say divided by 0.25. Oh, is my thing lagging? Why is my chat lagging so much? Sorry, Mr. Here, let me put this here so I can see it. Okay. No, you can go over. You can ask me whatever you want, Sib. It's totally cool. If I'm here and I'm not currently answering another related question to what we're doing, you can ask about future stuff. I'm happy to go over it with you. Yeah. Okay. So, again, 500 newtons. That's the force. Area is this, right? Pi r squared of the cylinder. And that gets you an answer, very big answer. This gets you 254. Oh, sorry, let me show you on my calculator what I did. 254. Let me just fucking copy it. And then I'll show you how I did this. They gave you way too much information here, Mistral. That's how they're trying to trick you. So, anyways, you get this. This is the answer after I do this. And then in order to get atmospheres, okay, 1 ATM is equal to 101 times 10 to the 3. So I just divided by 101 times 10 to the 3. And that gets you around 252 atmospheres. Okay. I think what they wanted to eventually show you here, right? Okay, is that so that pressure that is placed on the master cylinder. This is how a brake system works, a hydraulic brake system. It's actually really cool. That 500 newtons, and we're going to go over this in tomorrow's lecture, that you apply here gets amplified to being pushed on all the brakes. So here's the cool thing. That pressure here is the same pressure at any other part of the line. Well, I guess except for here, because now you're splitting the pressure amongst things. So if we want to figure out the force that's being applied here, watch. You could do, so that pressure we got, so 254 64790, right? 254 64791. That has to equal the force over the new area of all these cylinders. And I think it says there are 4 cylinders, right? And each cylinder has a diameter of 2.5 centimeters. Okay. So then this is divided by 4 times, and then it's pi times 0.025 squared, right? And so let's do some math here so we can calculate what the force is. So 254, so what that big ass number is. Oh, no, sorry. And then we're going to multiply that by 4. We're going to multiply it by pi. And then we're going to multiply it by 0.025 squared. And that's going to give me that 200,000. Wow. So, yeah, pretty crazy, man, right? So my 500 Newton force... Oh, then divide that by 4, because it goes to each cylinder, right? Yeah. It gets converted into 50,000 newtons. That's crazy. On each one. Yeah. Because what? That's a factor of 5 but then it's 5 squared, so it's 25. Is that right? Well, it should be closer to that. Ah, but there's a bunch of them. Yeah. And then it's times 4. Yeah. Wow, crazy. Oh, I did my diameter wrong, sorry. It was this. Oh, it's even bigger then. Oh, man. The cool thing, Mistral, that we're going to learn, we're going to learn it in tomorrow's lecture. I'll give you a little sneak peek for it. Anyways, the correct answer for this was just 251. I wanted to, like, show newtons-wise how, for instance, applying 100 newtons from your foot turns into 500 newtons being applied to what's called the master cylinder of a car. That has to do with torque. And then that 500 newtons gets multiplied into an insane amount of force on your brakes due to, I think it's Pascal's principle is what we call it. So let me see. Yeah, totally. Let me explain it to you. Well, okay. Did you understand this component here? Was this okay for you? I'll explain the new stuff, but I have to, like, kind of show you some other things. It's hard to show it on all these brakes, and then there's like 4 brake lines and everything. Yeah. Okay, cool. So you got this? Okay, awesome. All right. That's easy, right? You know, the pressure in the system here is just related to the force in the area on the cylinder. Yeah, okay. But then when we talk about the brakes, okay. So let me pull this up. It's a really cool part of the chapter. It's called Pascal's principle. Yeah. So, if you have 2 pistons that have different areas, okay? And the fluid in between it is incompressible, okay? Remember what we learned earlier about the barometers, right? Where, you know, they're at the same height, they're at the same pressure and stuff, right? So, whatever the pressure is here in this piston must be equal to the same pressure here in this piston, okay? So, that also means whatever pressure is here from some force pushing down has to also be the same pressure here that's going to be, like, pushing up. In this case, fluid is moving, okay? Like, we are, like, moving fluid this way. But, so, the pressure here, right, is going to be equal, so P1 is equal to F1, plus we would say, like, P atmosphere. And then P2 is equal to, I guess that's like P atmosphere. What do I want to do with this? I want to think how I explain this. Oh, never mind. No. This doesn't have atmospheric pressure. Sorry. This is sealed. Yeah, nothing's... Yeah, the atmosphere is not affecting the liquid here. Main thing is that, like, pressure here has to equal pressure here. And then let's talk about, like, pressure is. So, pressure is equal to force over area. Okay? So, P1 is F1 over A1. P2 is equal to F2 over A2. Alright? If the pressure here and the pressure here are the same, because it's fluid at the same height, right? Then F1 over A1 must equal F2 over A2. Now, what that means is that in this case, let's say this was my... What do we talk about it? This was my... The pedal cylinder. The pedal cylinder had a diameter of 0.5 centimeters. Okay. So I can say, okay, F1 over pi over, and then what was that? 0.5 centimeters. So that's 0.25 times 10 to the minus 2 squared. This is pi r squared. So this is the area of small cylinder. Must be equal to F2 over pi. And then this was the brake. The brakes, which I approximated as all 4 of these. Wait, where is it? Where did my phone? Oh, it's over here. Sorry. I said it was all 4 of these basically in like parallel. Which actually, I wonder if I can do that. Because technically I'm splitting the fluid between the 2. Okay, let's just assume it's just 1 brake pedal for now. Yeah. If we assume it's 1 brake pedal, and then this brake pedal has a bigger diameter of 2.5 centimeters. Okay. Now this is going to be pi times 1.25 times 10 to the minus 2 squared. Okay. So you should see something here, right? This is a much smaller number than this, right? Which means, in this case, when this was 500, that is going to create a bigger number over here. Or the other way to think about it is, if we were to rearrange this, this becomes that like F1 over F2 is equal to A1 over A2. Okay? So the ratio of the forces is inversely proportional to the areas. Or, so, as, let's think here. Yes, if this is smaller, well, okay, no. I like to think about, like, it's a magnifying effect usually. So usually we say this. We say F2 over F1. No, wait. Pressure. Wait. No, that's okay. It's not inversely proportional. F2 over F1 is equal to A2 over A1. Right, okay. So bigger area, bigger force. If this is set, if you have a set force and a set area on your first piston, if you then have a bigger area on your second piston, then you also must have a bigger force. And you can see that kind of with the math here. So if we were to solve for F2 here now, you would get that like 500. So first of all, the pi's would cancel, right? So this cancels with this. And then this is off by a factor of 5, right? But then it's 5 squared. So it's a factor of 25. Yeah, well, that's really cool. But whatever. I'll do the math. I'll do the math for it. It's okay. So if we do... If we do 500 divided by 0.25 e to the minus 2, and then we square it. We get some massive ass number. And then if we multiply that by this, cross multiplying it to get F2. 1.25 e to the minus 2. Good. You get 12,500. So now I would get that F2 is equal to 12,500. So applying a 500 Newton force on the smaller piston ends up multiplying by a factor of 25 to give you a 12,500 Newton force on this piston going up. Because as you're pushing fluid down here, the fluid has to go somewhere, right? And so it has to go up. And that creates a force on this upwards, which creates a pressure there. Yeah. We're going to learn that tomorrow. That's Pascal's principle, is what it is. How long is Physics 2 this summer? It's 6 weeks. It's very fast, honestly. So we didn't care about the 100 newtons from the break. Yeah, we did not. They just said that the 100 newtons here translated into 500 newtons being acted in that direction. Which, I mean, we can kind of... So, I assume this is the pivot point, is what they're saying. And then, the problem is, like, this 500 newtons is being applied at an angle. Because we remember from mechanics, right? If this applies a torque this way, and let's say it's, you know, steady, then this must apply a torque. Well, no, it's moving is what it is, right? Oh, I see. But pulling it out is going to apply a force that way. Oh, I see. There's force from the cylinder trying to keep it in. Okay, one sec. Or no, okay. This diagram's all wacky, dude. Okay. This is what happens. When you press here, this moves this way, right? Which creates a force that pushes it in that direction. The issue is all the angles. I'm trying to think of all the angles. So, first of all, I would need to know... I need to know the perpendicular force here. Like the 100 newtons is being applied at an angle. Maybe we assume that because it's connected here, it's the same as if it were right there, maybe? I just want to see if the math works out to 500. So, RF1 has to equal RF2, right? So R1, F1 has to equal R2, F2. Let's assume this is located, yes, 20 centimeters from the pivot. So I have 0.2 times 100 has to equal my new force, which is going to be located at 0.04 times F2. And let's solve for F2 here. So 0.2 times 100 divided by 0.04. Aha, 500. Yeah. So this does exert 500 newtons in that direction. Interesting. I think we're assuming that the 100 newtons being applied here is like and then eventually linear and it just looks like that. And then this is the rotation point. Yeah, it's a lever. It is a lever, I guess, right? So, yeah, Fembox, I guess you would know better from engineering, right? If I know I'm applying this technically at an angle, But I guess it translates to it being horizontal, like right there. But yeah, that's Mistral. That's why they get the 500 newtons. The 100 newtons by torque then causes a force of 500 newtons there. And then that 500 newtons, yeah, from pressure is force over area, yeah. So here's my question, Fembox. I was able to solve for instance, if it was a single piston on the brakes, and I got that was 12,500 newtons. Would I multiply that by 4, since there are 4 cylinders, for like the total force? Yeah, not sure, right? Yeah. Let me see if I can see this question. Because, let me think. In my mind, you're 4xing the area. So what's going to happen is you're going to decrease, of course, each one is going to go less of a distance. That's the other thing. Some people think like this violates conservation of energy, right? For like, you're like, wait a minute, what? How do I get a force multiplier from applying a small force here and getting a big force here? The difference here is that energy, which is equal to work, is equal to force times distance. Right? F times D. So you have to move this thing a lot of distance to get this to move a little bit. Because if the force goes up, then the distance has to go down. Just by conservation of energy. Yeah, okay. Yeah, so because so here's the interesting part. Yeah, it's one piston by 4 simultaneously, right? Yeah, but you don't quadruple the area. So what happens is this amount of fluid though, right, is getting split now between 4 things. Oh, I see. Yeah. One sec. Let me get my picture. So this, Femvox, this is kind of what it's like, right? So it's like you have this. No. And then you have this. Yeah. I think this, yeah, this is the way to think about it, right? And it's not that this pressure is equal to the total of this pressure. It's that this pressure is equal to this pressure, which is equal to this pressure, which is equal to this pressure, which is equal to this pressure. Good. Okay, cool. I think that's the way to think about it. Yeah. Yeah. So each one of these is 12,500 newtons. So yes, you do get an effective 50,000 newtons of braking force. Wow, really cool. That was pretty fun. Yay! Nice. Okay. Cool. All right, I think that's good for today. I'll have more office hours tomorrow. I have another lecture tomorrow I gotta do. But I appreciate you guys all coming by. Appreciate all the follows. Thanks for the raid, Don. You the man. Yeah, if you want to keep learning physics with us, we're gonna be doing this all summer. So please feel free to come on by, refresh some physics skills, learn along with us. Really cool. Okay. Let me go see what channel we're gonna go raid. Yeah, who's on the Twitch today? 12:30 p.m. Yeah, that's when I teach my classes at 12:30 p.m. 12:30 noon. I'll put it on the calendar. Yeah, 12:30. Gotcha. Cool. Okay, nice. Let's see. Let's go say hi to Nerduino. He's a cool guy. All right. Thanks everyone for coming. We'll see you tomorrow. Office hours are going to be an hour later, so that's at 5 p.m. Pacific, 6 p.m. Mountain, 7 p.m. Central, 8 p.m. Eastern. Enjoy the rest of your Tuesday, and we'll see you around. Peace.